So today's learning talk will be a follow-up to Chip's from Tuesday, where he discussed the design implementations and what was considered when Deephaven Learn was built. Chip did a great job of discussing the motivation and the design implementation and everything that was taken into consideration. I'll be talking a little bit more today about real-world use cases and extending a little bit more on the design implementations that Chip had started talking about. So again, motivation for it is that prior to Deephaven Learn, we didn't really have a defined way to perform artificial intelligence, machine learning, and data science algorithms on Deephaven tables with our Python API. These type of stuff can be done without Deephaven Learn, but it's kind of messy and requires a lot of bookkeeping and is kind of clunky. So there are some challenges when it comes to this, and one in particular is the boundary between Java and Python. Our Deephaven tables interact, they store data in the form of Java variables, whereas when you are using Python, Python modules such as TensorFlow and SciPy and scikit-learn and that stuff all expects Pythonic data. So there has to be a way to convert the Deephaven table data in Java to something that Python can use, and then back to that Java data when you have results that you want to store in a resultant Deephaven table. So the solution is Deephaven Learn, which was built with a gather, compute, scatter paradigm. Chip discussed that on Tuesday. I'll be going back into that briefly here. So the idea is that you can transfer data from Deephaven tables to Python objects, namely NumPy arrays, using the fastest and quote-unquote chunkiest methods available. In addition, we support typecasting after the calculations so that if you expect your calculations to give results in integer, byte, or any other Java primitive, we support that typecasting. So the gather, compute, scatter paradigm is the principal design concept for Deephaven Learn. There are 3 steps, as the name would suggest. The gather step is where you take your Deephaven table data in Java and you convert it to Python. Deephaven Learn comes with another submodule called Deephaven Learn Gather, which converts your table data into a flat buffer, which can then be converted to a 2-dimensional NumPy array. We're also looking into, as for the future, converting to n-dimensional NumPy arrays, but that's something that's going to take some serious consideration and work to get up. So for now, we convert to a 2-dimensional NumPy array in which an end user can convert to whatever other Python object they need, whether it be a torch tensor or a TensorFlow tensor or a Python list or anything else. The second step is the compute step, which is really where the magic happens, where the users get to implement their AI, ML, and data science models on the gathered data. Deephaven Learn is agnostic to what the users do to that data, because it's at this point that everything is done within Python. The only thing Deephaven cares about is the output of your model, if it exists. As long as you can convert the output of your model will translate into something that can be stored in a Deephaven table, you're good to go. And then the final step is the scatter step, where you go from Python back to Java, where you convert your output data back into something that can be stored and displayed in a Deephaven table. So this allows for users to craft real-time solutions in Python for data science, AI, and machine learning. The model itself utilizes Deephaven's table update model, which means that it works well with both static and real-time data. However, solving real-time problems is more challenging than static problems just due to the real-time dynamic nature of the data. And I'll cover that when I go over some actual code examples. But we'll see that with Deephaven, it kind of makes that transition from static to real-time data a little bit easier and less of a kind of a shock to somebody like myself, who prior to using Deephaven pretty much only ever worked on static Python code. So as far as the problem solving, the flow that I like to use when I am doing this type of work, it's a fairly standard software development life cycle, where I first kind of have to brainstorm what I want to do. I then have to consider what my inputs are going to look like. One important thing to consider when it comes to Deephaven Learn is that when using Deephaven Learn Gather to convert table data into a NumPy array, a NumPy requires all data in a single NumPy array to be of the same data type. So if you are going to gather a subset of rows and columns from a table, you have to make sure that if you are going to gather them into one NumPy array, that they must be all of the same data type. If you want to convert data of more than one type, you can simply convert it to multiple NumPy arrays. You then must consider what kind of calculations must I perform. This step is tougher to consider for real-time problems because your calculations have to keep up with the real-time nature of your data. If your calculations are slower than the data feed itself, then your solution is just not going to work. Next, you need to consider what kind of output your model is going to generate. Like I've said earlier, as long as that output can translate into a Deephaven table, we'll see a little bit later in this presentation that it's fairly simple to go from that Pythonic output data back to something in Deephaven. And then once again, performance is how fast is my solution and will it keep up with my data. For static data, that's not as much of an issue unless, as I found out, you train deep learning models. In particular, deep Q learning seems to take forever. So I'm currently looking into and hoping to get some content out about accessing GPUs as well as resources in the cloud in Deephaven to help speed that process up. So we'll get into some examples now. First, I'll just show some syntax that I'll kind of gloss over as I get through the examples. So Chip had shown a couple of these in his presentation a couple days ago, and I just want to go over those again. So when using Deephaven Learn, you need to specify a couple of helper functions, a model function, an input table, an output table if your model has output, and a batch size. The learn function itself takes 5 input arguments. The first is the table that is the source of your data. You then need to, again, craft a model function that will take some inputs and possibly have output. When using Deephaven Learn, you'll specify a set of inputs. That set of inputs must be an iterable object. In the case of this example, I have a single element list. And each object in the iterable must be a learn.input object. And each learn.input takes a subset of columns. In this case, I've used as an example columns X, Y, and Z. And then that second argument is a gather function, which I'll go over shortly. And that gather function will specify the rows and columns from which Deephaven Learn will take from the table. Next, you specify your outputs, which, just like your inputs, you need an iterable object of output columns. In this case, I'm assuming my model has one output, so I specify one output column. The next argument is my scatter function, which I will use to scatter data back into a Deephaven table. And then the third argument will be a string, which will be some Java primitive, whether it's int or double or long or whatever you want the output of your model to look like. The last argument is the batch size, and Chip covered this in greater detail on Tuesday. I won't go quite into as much detail other than when doing real-time data processing, your batch size should be specified as the maximum amount of data you expect your model to intake in a single update cycle. So if you expect 100 rows per second to be written to a table, your batch size should be 100 or possibly slightly higher. If you ever expect that number to increase. So I just went over this briefly, but each learn.input object takes 2 input arguments. The first is one or more columns from the source table to gather data from, and the second is the gather function that specifies what data will look like. So I have 2 examples down below. The first is where I take a single column, and the second is where I actually have 2 learn.input objects stored within a list. In which case, when I feed this to my model function, the model function will actually see 2 inputs instead of 1, where the first input will be a 2-dimensional NumPy array with 2 columns, and the second will have 1 column. As far as outputs go, I also just mentioned this, but each learn.output object takes 3 arguments. The first is the name of the new output column. The second is the scatter function that will specify how that data gets scattered back into a table. And the third is the data type of the output itself. If your model has more than one output, generally speaking, you should specify you may need to specify a unique scatter function for each one, particularly if the output of your model is multidimensional data, and because you need to tell Deephaven which data point at which indices it will grab and place back into the table. And again, the batch size will determine the maximum number of rows that will be gathered for processing at a single update cycle. So for static data, Chip had mentioned you need to take into strong consideration what kind of processing unit you are using, whether it's a CPU or a GPU or a TPU or some cloud processing equipment that you have access to. As far as static data goes, it's best practice to feed the model as much data as your processing unit can handle in a single update cycle. That will result in your model training as fast as it can. Additionally, you can train it with smaller data sets. The batch size can have a minor effect, particularly on machine learning and AI models, and it will also affect the training time for your models. As far as dynamic data, again, batch size should be chosen as the maximum amount of data you expect your model to handle in a given update cycle. For problems with higher amounts of input data coming on every update cycle, you do need to strongly consider how much data that your model can handle. So that's it for the presentation. I'm going to just go into some code examples now. So I have a Deephaven session up here, and what I'll be doing is going through a portion of the NumPy demo notebook we have on our demo site. If you would like to, you can run this yourself. The notebook itself does a lot of the explanation that I'll be giving right now. So without further ado, we'll get right into it. What I'll do here is, let me actually make the text a little bit bigger. Hopefully that's a little bit more readable. So I'll first create an empty table with some dummy data. In this case, I will be creating a table with a cyclic signal that has added noise. In the real world, the noise likely won't. I just ran this earlier. Let me. Oh, that's why. That's why it worked earlier. I already had NumPy imported. So anyway, when I run this, I will create a table with some noisy data. I also plot it just so we can see what it looks like. I'll move the plot up so it's a little bit more visible. But basically, I have a cyclic signal, which is the sum of a few sine waves of different amplitudes and frequencies, and I add some noise to it. Again, in the real world, your noise probably won't look this nice and uniform. I mean, it's pretty obvious to me when I look at this what the signal looks like underneath the noise. But for now, let's assume that I don't know what that is. So moving forward, let's say one of our end users has a noisy signal like this, and they want to remove the noise from the signal so that they can feed the smoothed out signal to some model down the line that will do some processing. So if I try to do this without Deephaven Learn, I will, using a basic table operation, I will only be able to operate on one data point at a time. Not only that, but I can't really do much with one data point at a time. And so my best approximation would be to quantize the signal by rounding each noisy point to its closest integer neighbor. And when I run that, we'll see that that just really doesn't work very well. I could definitely do a better job with table operations by having some global variables where I store multiple values, but that would get messy fast and isn't really a scalable solution for bigger data, as well as problems where a developer will need to implement more than one processing routine. And once again, yeah, this just, obviously doesn't look very good. It quite frankly doesn't really look any better than the original signal. So enter Deephaven Learn. So Deephaven Learn allows me to operate on a subset of rows and columns at a time. And in this case, I'm going to just show the importance of the batch size, or really how the batch size works. So in this case, I don't actually do any processing here, but I will be using a quote-unquote model function to print the number of rows and columns being processed, or being, again, processed by Deephaven Learn in a given update cycle. So I have a couple of imports here. I import learn and learn.gather from Deephaven and Deephaven Learn. My model function will simply print out the number of rows and columns being fed to it at every update cycle. I have a gather function here, in which so our gather functions will always take two inputs. That is a subset of rows and columns from the table, which I here aptly call rows and columns, and then I will return the output of the table to NumPy 2D method of our gather submodule. And that table to NumPy 2D method will convert Deephaven table data into a two-dimensional NumPy array. In this case, I use this particular method can take up to 4 arguments. I use 3 here. I have the rows and columns that I specified as my function input, and the third argument is the data type of the output. So as we can see here, my table data, the X, the Y, sorry, I want data table. The X and the Y columns are both of double type, so I'm going to specify NumPy's double data type. There is a one-to-one correspondence between Java primitives and NumPy data types, with the exception of Boolean values. NumPy stores Booleans in kind of a strange way, and I'm not 100% sure why. But either way, so I have everything I need, and if I run this code, we'll see a few printouts to the screen. In particular, we have, so this has 1,000 rows, and I specify a batch size of 101 here, just to show what the batch size actually means. And so every time we call this, or rather the first 9 times we call it, my model function gets fed 101 rows and 2 columns. However, on the final call, we've processed 909 rows, which leaves only 91 left in the table. So on that last function call, we don't actually get 101 rows, we get 91. This is just to show that the batch size means that that is the maximum number of possible data points or possible rows that can get processed at once. If it gets fed less, that's totally fine. It will still handle it. So that's why in real-time data, you want to pick your batch size as the upper bound of the amount of rows you expect to receive in one update cycle. So back to let's do some actual data processing. Previously, I had quantized the signal 1 data point at a time by rounding to the nearest integer. This time around, I'm going to use a model function that will simply return the mean of a given window of data. So I have to specify a new helper function, which is my scatter function, which will tell Deephaven how to place the result of my model back into a table. And the scatter functions can usually be really simple. So in this case, I call it NumPy to table. I feed it a data and an index, which is the 2 arguments that your scatter function should always have. And because the output of my model will be a one-dimensional NumPy array, I will simply grab the item in the NumPy array at a specified index. And Deephaven will know what this index is as it goes through. So that's all we need there. Again, my model function will simply quantize a signal by calculating the mean over the given window. And then when I run this, we'll see that this works. And so I feed it a batch size of 20. So basically, I'm quantizing the signal by flattening the signal at every window of 20. We can see the green, which is kind of hard to see here, but if I remove the raw signal itself, we can see that I now have this quantized signal that, I don't really know if I'd say this looks better than the input signal, but hey, it's doing something. So let's go to something that works a little bit better. We're going to do something called a rolling ball filter, which can be implemented in NumPy. I want for this demonstration to not be using external Python modules, not a part of Deephaven's base installation. I gave a Learn talk a few months ago using scikit-learn, and I hope to give more in the future on other modules, but for now, I want to focus on the usage of Deephaven Learn itself. So once again, I didn't actually need to specify this scatter function here because I just specified it in the previous but we'll use it again. So I have a scatter function, and my rolling ball filter will be implemented in this rolling ball function, in which case I simply convolve the signal with a one-dimensional NumPy array that contains 1 divided by the length of the array itself. And this rolling ball filter, we'll see, will actually smooth out the signal. And what it does basically visually is if you drop a ball on this noisy signal and allow it to roll over and flatten stuff, and then you pick up the ball at every batch size and you drop it again. So, and if we filter out the raw signal here, we'll see that this one actually starts to work pretty well. But there is a problem here in that we can see some dips. And this is because of how Deephaven Learn works with its batch size. So I specify a batch size of 100, and with 1,000 data points, that means that basically what this filter is doing is I drop a ball on the first 100 values, I let it roll over and smooth it, I pick the ball up, and I drop it again. And so what we'll see is discontinuities in this filter at points where one batch translates to the next. And there are ways to mitigate this, and I will probably try to cover those in a future session. But for now, we'll see with all of the other implementations that this is the case. And so with the rolling ball filter, it works pretty well. So let's take it one step further, and we're going to do a polynomial fit to this noisy data. And so NumPy has built-in polynomial fit methods that are really easy to use. In this case, I'm going to specify a polynomial of order 3. So it's ax cubed plus bx squared plus cx plus d. I use NumPy's polyfit method to determine the coefficients a, b, c, and d, and then I can use NumPy's poly1d method to evaluate the polynomial at a given point. And so when I run this, we will see that the fitted data looks even smoother this time. However, we will notice once again that there are discontinuities at the edge of each batch. So if I filter that out, we can see once again there's a little discontinuity here and there, and it's because we're not enforcing continuity in between the batches. But again, this signal, if we actually look at the raw signal versus the polynomial fitted signal, the raw signal looks remarkably like the not noisy input data. And so I have one more script, and this script is to show that this will work in real time, because up until everything I've shown so far is cool and everything, but really it's not all that special until we get to Deephaven special sauce, which is handling real-time data. So what I'll do is I'll set up a data feed that will write the same noisy signal over and over. I think it will write 30 points per second, and then I'll implement the polynomial fit in real time using the same helper functions that I've already used. So what's nice about this is that Deephaven makes the transition for this particular problem from static to real-time data very easy. I can use the same gather and scatter functions that I've already specified doing my static data, and then all I have to do is apply the polynomial fit function I've already specified, as well as the helper functions that I've specified to the real-time table, and we'll see that the data just magically works. I also specify a batch size of 100, and that's more because even though I'm only writing 30 rows a second, in the case of some surprise, I would rather be able to handle more than 30 rows at once. So if I run this, we'll see that the plot as well as the table is updating in real time, and I have fitted values. And I can highlight just the polynomial fitted signal or just the raw signal or anything else. And that's pretty much it that I have for today. This may be a very simple problem to solve, but this methodology does translate well to much more complex problems, including ones in AI. I didn't show it here, but in the case of using Deephaven for AI, you can either choose to fit or train your AI and machine learning models to, sorry, it's not 30 values a second. It's actually, I write for 30 seconds and I believe it's actually 100 values per second. Either way, So when you train AI models, you can choose to train them on Deephaven tables and use Deephaven Learn, or you can train them on whatever Python object you like, whether it's a pandas data frame or a NumPy array. And then you can implement those trained models on real-time data stored in Deephaven tables using the methods that I've just described. Does anyone have any questions?
Sorry, JJ, you mentioned something about mitigating the dips in between the batch sizes. How would you go about mitigating that?
Sure. So the way I use Deephaven Learn here is that when you specify a helper function, in particular the gather function, which will tell Deephaven Learn how to take data from Deephaven tables into NumPy arrays, it does it in chunks, in batches. And so I've actually written a couple of examples that can mitigate this. The first is you can use AI and machine learning to enforce the continuity for you. In particular, scikit-learn and SciPy have some methods that enforce continuity in between batches that are being processed. So that's one approach. The other is you can actually do rolling window operations with Deephaven Learn. And that does require some management of Python objects to handle those windows, but I've actually implemented this for one of our end users doing financial analysis who wanted to do some rolling window Bollinger calculations, like Bollinger Bands and upper window values and lower window values for that. And so when you do that, you can actually what you have to do is when you call Deephaven, when you use Deephaven Learn to this particular batch size, you'll maintain a window of values where you can roll the new values in during every batch, and it will actually keep the previous values from previous batches depending on your window size. And when you do the processing and include those previous values, it's much easier to enforce continuity.
Cool. Very cool.
Do you want to say anything about your the gather function and pulling stuff into NumPy arrays, or do you think that's better for a separate discussion?
That's probably something we could go into a little bit more in detail for a separate discussion. I will say that we, by default, gather data into NumPy arrays because they're supported natively by Deephaven. And NumPy arrays also serve as the backbone for a lot of other popular Python objects, such as pandas data frames, TensorFlow tensors, PyTorch tensors. So once you get the NumPy array, it's fairly easy and fast to convert those to the object that you need in order to implement your model.
Right. Any other questions? All right. Thanks, JJ.
Yep. And if anybody wants to try this for themselves, this is all on our demo site. It's in the data science and AI folder. It's the NumPy and Deephaven notebook. So this is all available online at demo.deephaven.app.
Great. Thanks.
Thank you.